Good morning, everyone. My name is Verla Manikanta. I am pursuing BTech second year in Electronics and Communication Engineering. Today, I am going to explain what I learned during my internship on EV dashboard and ADAS warning system. During this internship, I learned about embedded systems, STM32 microcontroller, and embedded C programming, sensors, and hardware-software integrations. Okay, let's see next slide. EV dashboard and ADAS warning system. EV means electric vehicle. The dashboard displays important information like vehicle speed and SOC, motor temperature and battery and obstacle distance. ADAS means Advanced Driver Assistance System. It helps improve vehicle safety by detecting obstacles and giving warning to the driver. And in this project, the STM32 controller collects sensor data, processes it, and displays the output. Let's see next third slides. The microcontroller name is STM32F103C8 and T6. It is the main controller used in our project. It acts as the brain of the system. It receives input from the sensors, processes the data, and gives the requirement output. It has features like GPIO. GPIO means general purpose input and output, and ADC, UART, timers, and memory. During my internship, I learned how to program this microcontroller and interface different components with it. Let's see next slide. STM32 Cube IDE is the software used for programming the STM32 board. We use it to write embedded C code, configure pins, compile programs, and debug errors. It helps to develop and test the complete embedded applications. Let's see next slide. PiximLab. PiximLab is a simulation software used for testing embedded projects. We simulated the STM32 board like Blue Pill and connected different components like potentiometers and sensors. It helped us test the program and finding errors and verify the project without physical hardware. Let's see next slide. Potentiometers inputs. We used our potentiometers in our project. The first one represents the accelerator pedal, which controls vehicle speed. The second one represents the brake pedal, which reduces speed. And the third one represents the battery SOC. And the fourth one represents motor temperature. These potentiometers produce analog values. So we used analog to digital converter that the STM32 can understand. This only ADC means analog to digital converter. Let's see ultrasonic sensor. The ultrasonic sensor is used for the obstacle detection. It sends ultrasonic waves and receiving the reflected waves from an object. Based on the time taken, the STM32 calculates the distance. This helps in providing warnings and improve vehicle safety. Let's see next slide. UART and virtual terminal. UART is the communication method used to transfer data between STM32 and the computer. We used a virtual terminal to display the output values. It shows parameters like speed, battery percentage, and motor temperature and obstacle distance. It also helped in the debugging the project. And the last slide, project requirements and tools. The hardware requirements include STM32F103C8T6 board, potentiometers, ultrasonic sensors, and laptop. The software tools include STM32 IDE, PiximLab, Embedded C, and Virtual Terminal. These tools helped us design, test, and debug the project. That's all. The conclusion is through this internship, I gained practical knowledge about embedded systems. I learned STM32 programming and ADC. It means analog to digital converter, UART communication, sensor interfacing, and simulation and debugging. This experience helped me understand how real-time embedded applications are developed. I will open STM32 Cube IDE. Wait, it will take some time. Now I shall show my code. Wait for some time. These are the files required to our project. Now we'll see the microcontroller STM32 F1R3 C8T6. Wait, I will show. Yes, take some time. Yes, this is our microcontroller used in this project STM32 F1R3 C8T6. Now I build the project. Wait. Yes, the code executes with zero errors and zero warnings. Now I will open the PixSim lab. Yes, this is the blue pill board and this is the microcontroller, and we load the binary file, and this is our binary file. Will open. Yes, it open. These are the square parts. These are the potentiometers. These three are the ultrasonic sensors. The first one represents the front and this left and right. These are the virtual terminal. Uh, the input is given using potentiometers and the output is displayed through the virtual terminal. The first potentiometer represents the acceleration pedal, and when I increase the acceleration, the STM32 reaches the input using the ADC and the vehicle speed increases. You can see the speed value in the virtual terminal. Wait. Speed 21, 22, 22.9, 23.4. Yes, it increasing. When I decreases acceleration and increase brake pedal, wait, I will show virtual terminal. Speed decreasing, wait, yes, 24.2, 23.9, 23.3. Speed decreasing. Now I increasing motor temperature. The fault alarm shows. Yes, LED blinks. Fault showing one. Fault showing one. Okay, it's working. When I increase brake pedal, the speed decrease. The speed of the vehicle decreases. Okay. This potentiometer is used to simulate the battery state of charge. SOC means state of charge. Now I will demonstrate the ultrasonic sensors. This sensor is used to detect in front of vehicle if it sends ultrasonic waves and measure the distance of obstacles. See, I will decrease this left and right. The blind spot detects. This is the left blind spot. This is the right blind spot. If I decreases motor temperature, wait, I'm decreasing motor temperature. So degrees. See, right blind spot off. I'm increasing this. Left blind spot stop. I'm increasing critical alarm also stop. Now I open the command prompt and give the command and enter. Wait. Now the dashboard is open. Yes, this is our dashboard. On the dashboard, we can see different parameters such as vehicle speed, battery percentage, motor temperature. Yeah, this is our motor temperature. Time to collision. This is our time to collision. And board view, advisory messages, and fault detection. First, I will increase the acceleration. Wait. I am increasing already increased. I am increasing the acceleration pedal. As the acceleration value increases, the vehicle speed also increases. At same time, the battery percentage decreases because the vehicle consuming battery power while moving. See, battery decreases 36.2, 36.0. Battery decreasing, speed increasing. 58, 59. Yes, speed increases correctly. Now I increase the brake pedal and decreases acceleration. Wait. Now I decreasing acceleration pedal and increasing brake pedal. Let's show in dashboard. The vehicle speed decreases. See, wait for some time. It takes some time. Yes, it decreases from 60 to 59% and increases battery percentage because our project uses regenerating braking systems. During the braking, some of the energy is recovered and stored back in the battery. Wait, 35%. Speed decreasing 55. Yes, 35.1. Battery charges during braking because we use regenerative braking systems. Next, I will increase the motor temperature. Wait, I am decreasing this, increasing this, and I am increasing motor temperature, showing fault alarm, and the vehicle stops automatically. This is done to protect the motor and the vehicle from fire accidents, etc. Yes, I will show false one to one. Now let us see blind spot indicators. The dashboard continuously monitors the front, left, and right sides of the vehicle. If any obstacle is detected in any of these directions, the corresponding indicator is activated to alert the driver. Wait, let's see. Fault. I'm decreasing motor temperature. Fault is off. I'm decreasing. See, right blind spot detection is on. I'm decreasing this. See, left blind spot detection on. We see on the Python dashboard. See, our EV dashboard is closely to the obstacles near the left and right. Alarm advisory. Alarm advisory. Now I am increasing this. I'm also increasing this. I am decreasing this critical alarm because see, wait, 106. See, our vehicle is closely to the front front vehicle. Time to collision is 0.0 second. Alarm shows critical and the alarm shows critical and the background see how blinks red and black. It shows critical alarm. See, red light blinks, blows. As you can see, all the dashboard values are updated in real time based on the inputs. This demonstrates that the EV dashboard and ADAS warning system is working correctly. Thank you very much.